Welcome to this session of Data Summit Connect. I'm Mary D. Ojala, Conference Program Director for Information Today, Inc. And our session today is Architecting Data Lakes for the Modern Enterprise. So our first speaker will be Nishith Agarwal. He is Engineering Manager for Uber. He leads the Hudi project at Uber and is a PPMC on the Apache Hudi incubating project. Following Nishith will be Inessa Gerber, Director of Product Management for Denodo, who is the sponsor of this session. So I would like to thank Sumo Logic, who is our diamond sponsor for the entire conference. And I will now turn over the so-called podium to Nishith Agarwal. So Nishith, if you want to share your screen and unmute.
Welcome, folks. My name is Nishith. I'm going to be talking to you about building large-scale transactional data lakes using Apache Hudi. A little bit of background about me. I am an engineering manager at Uber. I also work as an Apache Hudi PMC. A quick note, Hudi, a few months ago, graduated to an Apache top-level project from an incubating project. I will largely work on problems in the data world. How do you do standardized ingestions, schematizations, and build data lake primitives for use cases at Uber and in general. And I've added a couple of relevant blogs. I'm an active blogger. I blog about these kinds of problems, and added a couple of links here which may be useful once maybe the slides are shared. So before we dive into how to build them, let's understand what does a data lake mean. So a data lake is a centralized repository that allows you to store your structured as well as unstructured data. So you basically store your data as is, a one-to-one representation of the data from the source from where you might be pulling data into, without having to first structure this data into a different transform data, transform type. And then you can run different types of analytics on this. You can create dashboards, visualizations for big data processing, or build derived tables to build data warehouses to guide better decisions. So to be able to build a data lake, let's understand what are the canonical requirements from a data lake, right? So the first requirement is around incremental database ingestion. So think about you may have a table in some of your chosen sort of upstream databases. Let's take an example of MySQL, where you have high value information. Maybe it's user information, maybe it's business transactions about the businesses that you are running. And what you want to do is you want to replicate these business sort of high value data to your data lake. Traditional methods of doing this involve bulk loading, which is basically pulling data from these sources and putting them onto the lake. Those add a lot of load to the database and also do a lot of wasteful rewriting, depending on figuring out what data has actually changed, right? So if you take an example here, you have these tables like a user ID, country, last modified, and you want that represented in the data lake. Just to note that these are change data capture, which means you could have inserts, updates, and deletes, and you want to be able to track them and then be able to replicate that onto the data lake. The second requirement is around De-Duping Log Events. So think about if you have like an e-commerce website and you or an application through mobile app and you're producing impression events. And these impression events you want to be able to replicate on the data lake. Generally, these kinds of events are very high scale, several billions or even trillions a day in cases like Uber. There could be when you're trying to replicate these events, there could be multiple reasons for duplicating these events onto the data lake. For example, a client may retry, or there is a network error because of which you have to retry. Or your pipeline itself, the replication pipeline itself is only guaranteeing, at least once and not exactly once. And the side effects of having these duplicates is an overcounting problem. For example, if you have you're running a count on the number of impressions on a particular feature that you released, that eventually translates to the amount of dollar that that feature is making. Overcounting problems can be very nasty to deal with. And at the end of the day, it leads to low fidelity data because you can't really trust this data, whether these events actually happen twice or are they unique. So you want to be able to have a way to dedupe these log events. What do we do about storage management? So generally, you use like a large distributed file system to be able to store this data. In some cases like HDFS, small files are a problem, and they stress the file metadata. In some systems, you want to write big files, but then writing big files take time. For example, if you're writing a 2 GB Parquet file in a file format like Parquet, it would take about 5 to 10 minutes, depending on a fairly medium to complex schema. So one of the ways to solve this is, hey, can we just do file stitching? We write small files, we stitch them together, create big files. This way, you don't have delays in your ingestion pipeline. But then, this leads to a very non-standardized format of doing it. How do you maintain consistency between like the files that you wrote and the new files that you're writing? And has a ton of write amplification. So you want to be able to solve like some sort of these storage management problems that plague not just like systems like HDFS, but also other cloud stores. What are the scaling problems in terms of accessing distributed file systems? So when you access a particular file or a partition that you've stored on your DFS, you list those folders. Listing in some cases very expensive, especially like, for example, S3. You do single threaded versus parallel listing. And then there are many subtle gotchas in how you use a distributed file system. Some cloud systems don't allow appends. Some are eventually consistent. And in some, there is a name node that is a bottleneck, and you want to be able to scale beyond that. So how do you solve these challenges? The next one of the most important ones is providing ACID semantics on a data lake. So let's understand, what does ACID semantic even mean on a data lake? ACID, like A, stands for atomicity, which means that if an ingestion is running, it can fail midway. So either I provide everything that I wrote as part of that ingestion, or I provide nothing. Now that could be a single record, or it could be a batch of records. Generally batch of records in a sort of batch world. Consistency, which means only the valid data is saved, and every invalid data is rolled back, and the invalidity of this data can be defined by the semantics of the storage system that you're using. Snapshot isolation. So I stands for isolation. So you want to be able to only expose read committed data to users, while at the same time you can have concurrent writer and readers accessing that data. So you don't want to have data that is dirty be exposed to users, where different users get different values. And finally, you want durability, because we don't want data loss. And so meeting all of these requirements will help us create an ACID semantic data lake. The next requirement is around faster and derived ETLs. So we talked about data lake. It has this like huge repository of all the data that you replicate onto your offline data world. But a lot of times you have these curated set of tables that you either pull in from many of these raw tables and generate your downstream table, or you trim down a single table and generate your downstream table. A good example is you may have payments as a raw table, and you essentially want to standardize that payments into a particular standard amount. And you're creating a derived table based on that. So then maybe you have payments in different currencies, and you want to standardize them based on some metric that you have. So generally, these pipelines are multi-stage DAGs, very common in batch analytics. You have a large amount of data that you want to read, and you want to keep refreshing your downstream table as and when new data is available upstream. So some of the challenges are, how do you do these intelligent computations? What changed upstream? And how do you only change the parts that you want to change in your downstream derived table? And how do you do sort of window-based joins in these upstream tables? Let's say you're pulling in from like 10 other tables. Would you actually pull in everything from all of these tables? So that's a very, very critical challenge in solving, processing data on your data lake to build, other use cases and other derived tables. The next requirement is around compliance and data deletions. So, in today's world, there are strict rules on data retention, which records you want to keep, you want to correct, you want to delete, right? And these use cases spill over to any and all kinds of pipelines and tables that you may have on your data lake or the derived lake. You need so to be able to do that, you need some sort of pointish lookup to be able to do efficient deletes. But then at the same time, you want your workloads to be optimized for scans, because that's the majority of the bulk kinds of operations you want to run on your cluster. And eventually, you want to be able to propagate these deleted records to any and all users and consumers of tables downstream. And this way, you'd be able to build a really compliant system that handles data deletions and corrections end to end. To recap, like all of these requirements, we want to be able to incrementally ingest change logs, while at the same time dedupe really high throughput log events. You want to be able to scale and manage your storage on the distributed file system. You want to provide asset guarantees on the data lake. And you want to be able to do intelligent computations, not just for deriving tables, but also to be able to do data deletions. And finally, the data keeps, like, if you're absorbing data from upstream sources, there's always late arriving data, and you may want to update like records in the past. And how do you do that? So all of these are like requirements from the data lake. So now the question is, we have the requirements from the data lake. Maybe we can build a solution around it, but how do I build this data platform that can help me build the data lake, right? So the data lake is just part of the problem. You still need a lot of peripheral tooling around collecting data from these different sources. There is, your data, even though you stored it in some format when you ingested it, it may actually need to evolve based on usage patterns that you may have, either query patterns or access patterns. And then you want to monitor performance of data lakes. You want to monitor patterns of ingestion, correctness. So essentially, you want to build some data observability modules so that you can actually see what's going on and make sure that what you're doing is right and it's utilized to the best of the abilities. Talking about like maintaining all of these, we run into these problems of, okay, we have stream use cases, batch use cases, and now I have to maintain these multiple technologies, and there's a bunch of operational overhead. Is there some way we can sort of unify some parts of the stack? And so the question is there a single system that can manage and do all of these operations, but at the same time provide some sort of unification in stream and batch? So let's look at like requirements of the data lake, right? So you want hassle-free data ingestion. And ingestion has many challenges. You have multiple different types of sources: Kafka, raw file dumps, upstream. How do you build a system that just plugs in all of these components? You want to auto scale for spiky traffic, right? Or for maybe organic explosion and growth. You want to perform schema management. One of the important things of having a data lake with which you can use to derive insights is to have high quality, trustworthy data. And that starts at doing schema management to know what data you're ingesting. And then you need custom transformations, for different kinds of business rules, and sort of you want to update some table based on some sort of logic. And then at the end of the day, you want to provide observability and support different kinds of query engines out of the box, so that you can connect different kinds of query engines, access this data based on use cases you may have. I talked a little bit about unifying stream and batch. So let's talk about that a little bit more. So a typical Lambda architecture is, batch is great for slow moving data. It's, of the order of tens of minutes. And then, stream style processing is generally of the order of some sub-second latency. And then you generally use, you get stream data, you solve the use cases that you have for low latency data, but then you treat batch as your fallback, right? And there are different kinds of processing engines that you would use for that, and that's totally fair. But what about storage, right? So stream systems need some sort of specialized databases or maybe specialized systems, and are in many cases row-based, although some of them are also columnar-based, but in many cases row-based. And batch systems are generally columnar-based because they tend to be slower to write, but are really good and efficient for scanning. So what about use cases between 1 and 5 minutes latencies? Typically, at Uber, we realize there are lots of use cases that fall within this time bucket, and then there isn't a solution that streaming tends to be an overkill, whereas batch tends to be too slow. So is there an architecture? And there's a suggestion in the community that Okapa architecture is about unifying processing. But what about unifying storage, especially for use cases that lie in this kind of latency? And the final one I wanted to go over is, do you just write once and read many in a typical data lake? That's what we do. But what happens is you get stuck with the initial data layout, and they may not be best for your query pattern because that kind of layout may have been best for ingestion latency. And it may not be the most efficient for specific types of queries. For example, you want to query on user ID, but the data is actually split based on event time. So you want to adapt your data lake based on what are the needs of the data lake. So you may want to ingest fast, but then you want to reorganize your data based on query needs. And you want to do all of this without blocking readers and writers, so the business continues uninterrupted, but you keep tuning the efficiency of your data lake. So the question to think about is, do the data layout and query patterns have a strong connection? And in many cases, we realize they do. And this isn't a new concept, like databases, where you have online stores work this way. So at this point, I wanted to introduce Apache Hoodie. Hoodie is a system that helps you solve all of the kind of the requirements that I mentioned before. You can ingest data from different kinds of Kafka streams, change logs. You can create incremental streams on other Hoodie tables, just like what you would do for a Kafka stream. And then you'll be able to query this data using your preferred query engine, whether it's Hive, Spark, Presto, for interactive analysis or building incremental data pipelines. And finally, Hoodie tables can be stored on any cloud store or HDFS, basically any DFS compatible storage system. So if you were to look at a Hudi-based data lake, what does it look like? So you have these on the right-hand side, the diagram that's illustrating this. You have your upstream database service, raw events, and then you ingest them through a pub subsystem like Kafka. And then you can use a ingestion framework that Hoodie provides out of the box, which you can use to do ingestion, maybe at like close to 5 minutes freshness. The data lands on to HDFS, which is your your storage maybe, or maybe S3 or any other cloud store. And finally, Hoodie will expose different kinds of views over this data so that you can do time traveling, you can do scanning of data for columnar performance, or you can do real-time and incremental queries to build your dashboards and downstream pipelines. And finally, there are some components that asynchronous services that you can schedule using Hoodie, where you can adapt your data model, your data lake. I see there's a question. I'm unable to click on the Q&A, so I'll just keep going. Yeah, so the guarantee.
We can take the question later, Nishith.
Yeah, sounds good. So the guarantees that Hoodie provides are atomic multi-row commits. You only expose valid data to queries, and you can do a snapshot isolation using MVCC. And finally, the durability is provided by the durabilities of a distributed file system. So with all of these guarantees, you can achieve asset semantics on the data lake using Hoodie. So an ecosystem that you would use to build your data platform could look like this, where Apache Hoodie comes pre-built with a managed ingestion framework called the Hoodie DeltaStreamer. Hoodie plugs in different kinds of schema evolution like registries, and you can use Avro for that. We sort of unify batch and stream to provide that kind of like 1 to 5 minute latency that we're talking about. There's pluggable frameworks to provide data observability, and then we're working on making the data lakes more adaptive to take query patterns into account. And all of this obviously comes with the storage abstraction format, which is Hoodie, using row and columnar file formats to provide fast ingestion and highly optimized scan performance. So some of the use cases at Uber, I wanted to talk to you about first the facts and figures of like at what scale do we run Hoodie at Uber. So we have about 150 plus petabytes transactional data lake. The Hoodie manages about 10,000 plus tables, and we ingest more than 500 billion plus records a day. These numbers are a little bit old, but a couple of months old. So they may have changed a little bit. So a couple of use cases that Hoodie is used. So we use Hoodie to manage, to support like our entire data platform and manage all of our tables. But then there are other many use cases, within the company who use Hoodie for many different purposes. One example is, Uber's global network analytics is monitored in near real time using Hoodie DeltaStreamer. So think about the Uber app, running on different kinds of networks. There's 4G, 2G, LTE. All of these have different latencies which affect the performance of the application. So for Uber to look at, okay, in the global network, like where are the performances of this app being affected? That's the question. And the way the network analytics team solved it is we have these raw events that are coming in. These are network events. And then you plug in Hoodie DeltaStreamer to incrementally pull exactly what changed. So if you see the blue boxes, they transform these events and use some kind of reduced delta summary. They use something like T-digest to statistically map a higher order value of numbers to a lower order value of numbers, and then finally upsert that value into their summary table. And all of this happens in near real time, and they're able to actually monitor the whole network analytics with something on a storage system like Hoodie. Another use case which is very popularly used is like the Spark data source integration. So a lot of ETL pipelines are written. These are users who are more proficient in Hive queries and Python programming, and they use Hoodie and PySpark with Spark data source to do kind of the same thing that I talked about before, where they can incrementally pull from a source table, do some sort of staging table joins, and then finally upsert into a model table. Finally, I wanted to talk to you about some of the advanced primitives that Hoodie provides, which are useful, especially for maintaining sanity of your data lake. One popular feature that we use at Uber is to be able to recover from data corruption. So some of the common questions that we've had in the production systems in the past: what if a bug resulted in incorrect data being pushed to the system? What if an upstream system incorrectly marked a column value as null? There are different ways to achieve this, where you could have like type checking, etc., on your source. But what if you don't have it? So the Hoodie addresses these problems for you by providing a restore mechanism where you can actually go back in time to a previously safe pointed time for that table. And so Hoodie provides ways to be able to checkpoint your table at different instances of time. And then, for example, if you found some problem with your pipeline, you could go back to that state of the table, and users can continue to access that data uncorrupted. I talked to you about incremental processing. Just like these are two ways to actually use incremental processing in Spark and Hive. All you have to do is you use the Spark data source, provide the format as Hoodie, and then all you have to say is my query type is incremental, and I want to start I want to consume all the events that happened on this table after time, for example, begin instant time. And then you can basically get a data frame or data set, register as a table, and run your favorite types of queries on it. A similar thing is what you can do in Hive. It's just like with Hive semantics and primitives. And you can always do time travel queries with this. As you can imagine, if you can consume incremental events that happened after a particular time, you can say, hey, tell me the state of the table at the end of this time. And then you can basically keep time traveling back between different snapshots of this table. This is like sometimes very popularly used in in use cases such as machine learning, where you want to know what state of the model did you, what state of the data that you actually build this model for. And you can do it in different ways, Spark and Hive. And the Hive, the end timestamp is now implemented, so it should be available as of a couple of days ago, I think. Yeah, some other goodies, they're a very popular feature requested like across in the open source community is, can we convert our existing tables into Hudi tables? And recently we released a feature where you can very efficiently do this migration. All you have to do is this snippet of code, and you provide your source table name and the source table like path and the destination path, and this will very efficiently convert your existing table into a Hudi table. It will not rewrite any of the data. It will just create some sort of metadata and manage and create a new view on this table that will be managed by Hudi. There is a blog coming soon, so you'll be able to read about it. Finally, I wanted to go over some of the items in the roadmap. We are working on something called record level indexing. Indexing is used to figure out how to perform upserts. I talked about pointish lookups. Pointish lookups are generally possible, when you have some way to tell, hey, where do I go and look up this data? So we're working on a record level indexing to perform blazing fast upserts. One of the problems of slowness of upserts in like the order of minutes is because we use different kinds of indexing. We're working on adaptive data lake. I talked about that. We just landed a PR on abstracting out components to make Hudi engine agnostic, and a implementation of Flink with Hudi is on track. And finally, we are working on eliminating file listing. Most of the code is complete right now. It's in a sort of in performance testing mode, and hopefully by the end of the month we'll have eliminated file listing completely. That's all I had. I provided a couple of links here. You can reach us at dev@apache.hudi.apache.org. If you're interested, if you have use cases, feel free to send us emails or connect with us on the Apache org website. There's a link to the Slack channel as well. And it's a very budding community. Lots of exciting items in the roadmap ahead. Love to get contribution from other people as well.
Okay. Yep. Well, thank you very much. I think we will hold questions until the end of Inessa's talk. So if you have other questions, either for Nishith or for Inessa, do put those into the Q&A box. And so now let me move on to Inessa Gerber, who is part of Denodo's product management team. She works closely with customers and prospects to understand their products and requirements. And she is going to talk to us today about data virtualization. So go ahead, Inessa.
Thank you for the introduction. And today I would like to talk about a couple of different aspects. I would like to talk about business objectives. What are some of the difficulties and challenges in the data management itself? I'll introduce you to the data virtualization concept and how it fits into your enterprise ecosystem. And then we will talk about the hybrid deployment. We've been talking about cloud, we've been talking about data lakes, how all of the pieces fit together. There is more to the picture. Companies have more and more components within their enterprise. So first, let's talk about some of the objectives and challenges. So when I work with many clients, I see that they have several requirements. They have data spread across multiple systems. They do have initiatives in moving data into a data lake or Hadoop system, some other centralized location, but at the end of the day, they end up having data in multiple places. So how do you give them the single entry point to get access to all of the data? Also, how do you expose data to different consumers without involving IT? How do you nurture the self-service culture? And how do you do all of those in the secure and governed approach? So let's take a look at our data. Throughout the history, as we've been working with data, there are multiple data stores that have been taken place. You have the data warehouses, cloud, big data, and currently you have additional data coming from connected devices. All of the data stored somewhere, All of the data is collected, and companies continue to collect more and more data. But what about connecting all of the data? What about creating the data fabric, which will enable you to get access to the data? So this is actually what we see in many of the deployments. We see the data is spread out across multiple data stores in multiple locations. And a couple of the reasons there is that it might not be feasible to move all of the data into a centralized data lake. You have to consider cost, and you have to consider data ownership. You might have different acquisitions happening, which will prevent you from moving all of the data into a centralized repository. So in this picture, we have different consumers connecting to the data. You have your data quality tools reading the data. You have your data scientists connecting to the cleansed data, as well as the original data. You have your machine learning connecting to the data. And then finally, you have your BI tools accessing the data itself. So all of the products out there can connect and ingest data. But can they actually form business insights on top of the data? What if something changes? What if you continue moving the data into a different data store? It means that all of those applications have to change. So what we're looking to do is we're looking to centralize not only the data store itself, as we've been talking in the past, but also centralize data access, centralize security to access the data, and centralize the whole metadata management and governance of the data across any and all data sources, be that a data warehouse, be that an Excel file, be that a data lake, any data out there. And this is where data virtualization fits in. Data virtualization resides between your consumers and the actual data itself. So let's talk about what is data virtualization and how it can help us. So data virtualization becomes your centralized abstraction layer between the consuming application and the actual data itself. So first, data virtualization enables you to connect to any data source, any data lake, Hadoop system, anything out there. Once you establish the connection, you can create semantics model on top of the connection, and you can start connecting data together in a semantics model. You can deploy the solution in any environment. And since we are talking about data lakes, it's important to know that deployment usually takes place in an on-prem and cloud-based environments. But also, since we are simply connecting to the data, we are not moving the data, we are not copying the data, because data remains in its original location. It's important how we access the data. We access the data in real time. Since we're accessing the data in real time, we have to keep performance as top of the priority. So Denodo utilizes multiple performance enhancements. It utilizes query optimization, such as query pushdown, MPP processing, query rewrite. It also utilizes AI and ML internally to facilitate easy access to the data itself. And all of that is done with a centralized security and governance layer. So instead of having each consuming application connecting to your data lake, each consuming application is connecting to data virtualization layer, and data virtualization is connecting to your data lakes. So how do the consuming applications connect to your data? It really depends on what the consuming application is. You can simply connect using the JDBC or DBC bridge and start executing SQL queries. You can connect using APIs for web-based applications, or you can connect using the data catalog for self-service. So now let's talk about data lakes, and let's talk about our hybrid deployment into the cloud. As you heard being mentioned that moving data into a data lake is a common use case, and we see many clients actually taking their data and moving it into the cloud-based data store or into the Hadoop-based data store. Having that centralized repository takes time. It takes time to move the data. And in many cases, some data is still remaining in place deployed in the original location. So during that migration process, as the data is being moved across different locations, your consuming applications don't need to know any of the details. If your consuming applications are simply connecting to the Denodo platform, and the Denodo platform is propagating the connectivity and getting data from the actual data stores, the consuming applications are not changing, and all of the semantics is handled within the Denodo platform. But let's take it a step further. And this is a true implementation. This is something that we start to see more and more in the deployment, is where you have data sources on-prem, as well as you have data stored in the cloud. Companies are moving the data into the cloud. There is no question about that. But some of the data is still stored on-prem. So in this picture, I'm going to have Denodo deployed locally in my on-prem data center. Consumers are going to collect Denodo, and Denodo platform is going to query the data sources and get information back to them. Fully optimized, real-time querying of the information and getting the information back to the consumer. And then I'm going to introduce a new data store in the picture. Maybe there is an acquisition in the company and there is a new data store in the Azure Data Cloud. Not an issue. Instead of the consumers creating a new data link into the new data sources, Denodo is going to do it for them. So Denodo is going to consume data from a new data source, and then consumers are getting new data without implementing any change, without any knowledge of where the data is coming from. So what about the next step? Let's say I have a new data store. I have my European Availability Center. Am I going to continue creating new links to the new data stores? Is it really optimal? What about latency on the network? What about constantly querying the original data source? Well, in this picture, I'm actually going to have a fully hybrid architecture. I'm going to keep my Denodo instances locally in the on-prem data center. I'm also going to introduce Denodo instances deployed into the cloud-based environment. So when the querying is coming from my consuming application, it's going to parse the query. It's going to propagate relevant query information to other Denodo instances running close to the data. And then the local Denodo instances are going to get the data in real time in an optimized fashion and propagate the results back. So this enables me to reduce the latency as well as reduce the cost of data query and data propagation across the network. Again, consumers don't need to be concerned where the data is coming from. They don't need to be concerned if it's coming from a data lake, if it's coming from on-prem Oracle data source, or if it's coming from some Azure environment. So what is it actually giving me? Data stays in place. Data is not being moved. Data is accessed at real time. So as the companies implement the data migration across multiple environments, the consuming applications don't need to know. They're accessing the data through the Denodo abstraction layer, through this data virtualization platform. Denodo also can be deployed very quickly, so the time to market is quick. You don't have to have consuming application connecting to the data sources. Again, they're connecting to Denodo, and Denodo is feeding the data. So this seamless deployment is going to bring insights into the data much quicker to the consumers. But you know what? Instead of me going through multiple success stories and different use cases, which are all published online, you can simply go to the success stories on the Denodo platform. You can take a look at different use cases. There are multiple recordings, and take a look at how other customers are using it. Take a look at different use cases, from MDM to data lakes, to migration use cases, to data warehouses. How are other clients implementing data virtualization? And more importantly, and I think this is critical, You want to be able to test the product. Take the product for the test drive. You can use the test drive of the Denodo platform with your own data or with the prepackaged data. You can deploy it on any platform, be that AWS, on-prem, Azure, any cloud environment. See what you can do. See how you can connect all of the data. It's not only about collecting the data and creating the data lake. It's how you're going to access the data and how you're going to expose the data to your business consumers. So thank you, and this was a quick overview of the Denodo platform.
Thank you very much. Thank you. Let me remind people that if you have questions for either one of our speakers, do put them into the Q&A box there. This is the first question that came in while Nishith was speaking. So this question is, how is Hudi different from Unify? And then the second question, because it specifically says it's adding to the first question, how does Hudi differ from Databricks and Apache Iceberg?
Yeah, thanks for the question, guys. So let me answer the first one. From what I understand, Unify is more of a stream processing platform. So you can think of it as a connector between your pub subsystem like Kafka and a eventual sort of storage system like Hudi or any other storage system that you may want to choose to write your data into. I think it provides like transformations and connectors to be able to do that. So the best parallel that I can draw is like the Hoodie DeltaStreamer framework that I talked about. You could draw a parallel to Apache and Unify there. That is my understanding. The second question around how does Hudi differ from Databricks and Iceberg? So yeah, all of these projects have some similarities and some differences. So Databricks has it's a company that provides a platform to be able to do certain of the operations that I talked about, but they have a paid product and an open source product. And I'm not sure what they provide in the paid product. And in the open source product seems to be pretty vanilla. But don't quote me on that. You'd have to go and like try it out yourself. Iceberg, in my conversations, has been used as a metadata management for the data that you may write in your data lake. So you have your files. It does like metadata management. It does schema evolution for you. But then it like for example, the difference between Hudi would be Hudi provides many runtime engine components, like how do you do cleans, how do you do compactions, how do you do time traveling while at the same time have a retention based policy, how do you do deletes, how do you do upserts, these kinds of questions Hudi answers, and to my knowledge Iceberg does not. There may be a path to be answering that in those platforms, but I am not like specifically aware of them. Yeah, so those would be the differences. The one thing I'd call out is so I think the comparison here that I did is more from the Hudi storage format, but then a lot of other components that you get with Hudi is, which I talked about, the DeltaStreamer, like native like support of query engines, and some other of these goodies to build your data platform. Those are like components that you could use out of the box with Hudi, which I'm not sure how is done in the other two platforms.
Inessa, is there any difference when Denodo runs on the 3 cloud platforms that you showed? Is there any actual difference in how the Denodo platform operates with each of those 3?
Actually, no, Denodo is going to operate the same way. The query received from the consumer on the first Denodo instance is going to be parsed. It's going to be optimized. Denodo will check what type of data sources are in play, because you are getting information from multiple data sources. And it's going to pass relevant query information to other Denodo instances if data has to come from there.
Okay.
The local Denodo instance is going to optimize the query, get local information, and propagate only relevant results back to the original instance and the consumer. So it's all about the proper deployment and architecture where it depends, do you want to have one instance of the Denodo platform connecting to multiple data sources, or would you like to have a local Denodo instance residing close to the actual data itself?
And do you find that your customers now are much more inclined to migrate to the cloud than to have an on-prem? Or has it stayed kind of steady state?
Migration into the cloud is certainly a huge area. We see more and more clients moving into the cloud, but they are not taking a big jump. When you move things into the cloud, it takes time. They're going to move certain data assets into the cloud, but other data assets are going to remain in place. So this is critical when you truly have this hybrid architecture, that you are able to consume any data in real time without the need or without the requirement to actually move the data and have the ETL type of processes. Keep in mind, ETL and ESB are all parts of the ecosystem. So Denodo is not a replacement for those processes. It's an addition. So all of the products work together.
Okay, we're back to Hudi here. Does Hudi storage sits on HDFS, or is this a processing engine like Spark?
Yeah, so Hudi is a library, and it has something called a storage format, and then runtime engines that let you manage that data. So you could use your storage engine, like you could use S3, for example. Hudi comes pre-packaged in AWS. If you go on AWS and search for Hudi, it comes pre-packaged with it. So you can use any system like S3, any file system like S3, HDFS, GCS to store your data, and Hudi uses for all its runtime components, ingestion, cleaning, compaction, it uses a processing engine like Spark, and in the future Flink. So it's a library that you can use to manage data, and it's stateless. So hopefully that answers the question.
Okay. And here's one for you, Inessa. Can I apply data security at Denodo layer?
Well, the short answer is yes, absolutely. But to give you more content is, if you had consumers connecting to the data sources directly, it means that they have to implement the security layer every single time. When you have consumers connecting to Denodo, then the security layer is implemented within the Denodo. You can secure depending on the data store. You can secure based on the actual records. So we have row and column-based security which you can implement. You can do it natively in Denodo, or you can implement it and integrate with your single sign-on model, with your LDAP, Active Directory, any other existing security model which you have in the enterprise.
How does data security play into the Hudi environment, Nishith?
So Hudi itself, doesn't provide any semantics for data security, but the way I've seen it being used widely in the community and even at Uber, you have your file formats. For example, Parquet, it may provide you column level access control. And so you would define column level access control at your file format level, or you would define column or row level access control at the layer of your query systems, query engines. And so you basically would have like either a layer at the lowest layer, or a layer which like does RBAC, and then access control according to that. But Hudi is more about like storage management and doesn't get into access management.
But everybody these days is concerned about data security.
For sure. Yeah.
Whether it's appropriate or not, people are concerned about this.
Yeah, I think security and compliance and retention, I think these have become more and more important.
Well, they have, and you actually made the point about strict rules and data retention, and that all goes back to legislation, privacy legislation, and we've just all heard so much about data breaches and about identity theft and all the rest of those dreadful things. And so people get kind of wary about security, and particularly in a retail environment where people are worried about what's going on behind the scenes, because frankly, most of your customers haven't a clue about what goes on behind the scenes.
That's correct.
Let's see, do we have more questions here? Not at the moment. You know, when you were talking, Nishith, you were talking about data layout and query patterns. What happens when you notice a change in query patterns? And you see that, then how hard is it to change your data layout? Or do you have to go back to square one and start all over?
Yeah, it's a great question. So, you know, for the data lake and the data warehouse world, right? Like the way, you know, you build like large scale like systems like these, there aren't any tools available right now. We haven't even started to think about like how do we want to change the data layout based on. Generally, all of this is very static, right? And you can imagine in a large organization, if you have you know, tens and thousands of queries running every day, they are not going to be the same. And you don't know what queries they're going to access. So if you look at like how you would model a database, a table in a database, you generally say for example, for distributed databases, you say, hey, what kind of queries do I have? And can I model that table to suit that query pattern, right? But for data lakes, we don't do that. We just say, hey, can I get this data as fast as possible in all of the data? And I'm going to write them in a format that makes sense, right? And the format is great for actually reading that data, but it doesn't make sense on how the query gets translated to read that data. And that's the part that's missing. And that's where you know, you have to sort of take that feedback off the query patterns and see whether there is a more efficient way of laying out this data for your queries.
What does Denodo do about changes in user behavior?
Well, there are a couple of aspects. For us, the user is the actual consumer of the data. So if the user is using our data catalog, which is for the data steward, so they can actually see all the data,
right?
We actually utilize ML and AI internally. So we learn what user queries are, and we learn what other users in their group are doing. So we can provide suggestions on some of the relevant queries and information. So if I'm constantly querying for customer data, and there is a new data asset which has customer returns, I'm going to be suggested the data set within my data catalog environment.
Okay.
So when I log into my business portal, I'm going to see that, well, Inessa, take a look at this additional data asset. It has value.
Okay, very good, very good. Well, seeing no more questions here, you must have answered everything that they had in their heads. So that's wonderful. So I would like to thank, I'd like to thank both Nishith and Inessa for great presentations. Thanks to Sumo Logic, who's our diamond sponsor. Thanks to Denodo for sponsoring this session. And we have thank yous coming in the chat, so that's added to my thank yous. And for the audience, we will be running the next session for Data Summit Connect at 4 o'clock Eastern Time. And we look forward to seeing you there. And thanks again to our speakers.
Thanks, guys. And thanks, Meredy and Steve, for organizing and running the show.
Very welcome.
Thank you all.